Hi guys, today we're going to be multiplying and dividing with complex numbers. We're going to continue treating those imaginary units like variables, and if we get higher powers of I, we're going to use the properties we learned yesterday to simplify them. So let's get started. For number 14, we're going to distribute negative I to both terms in the quantity. So negative I times 3 gives me negative 3I, and negative I times I gives me negative I squared. So remember yesterday we learned that I squared has a value of negative 1. So I'm going to replace that I squared with negative 1. So I have negative 3I minus negative 1. And then this minus negative is going to turn into a plus. And then we're going to have negative 3I plus 1. Now technically complex numbers should be written with the real part first, so in the format of a plus bi, where the real part of the number is in the front and the imaginary part comes after. So technically we should rewrite this response as 1 minus 3i, although if you did it the other way I probably wouldn't count it wrong. This next one we're going to double distribute or FOIL. There's another method we can use called the box method or the area model method. I'll show that one on example 16. So for this one, I'm going to double distribute the 2 to both terms in the second quantity. So 2 times negative 6 is negative 12. 2 times negative 2i is negative 4i. Then I'm going to double distribute the 3i. So 3i times negative 6 is negative 18i. And 3i times negative 2i is negative 6i squared. Now every time you get an I squared, it is not necessary for you to rewrite the negative 1 there and multiply. It's okay with me if you take this little shortcut. If you want to just mark out the I squared and change the sign of your last term, because really what's happening here is you had a negative 6 times a negative 1, and that became a positive 6. That's a little shortcut that you can take so that you don't have to keep rewriting all the steps of the problem again. So now I have negative 12 plus 6, which is negative 6, and then I have negative 4i and negative 18i, which is negative 22i. This one I'm going to use that box method. So you're going to make a 2 by 2 box, and you're going to write the terms of the first quantity. Doesn't matter whether you write it at the top or on the side. So negative 3 and I. Just make sure you write both of these terms at the top and both of these terms together on the side. So 8 and 5i will go over here. And then in this box you'll be multiplying 8 times negative 3, and then 8 times I, and then 5i times negative 3, and then 5i times I, which gives you 5i squared. So you're going to eliminate your I squared and change the sign of that 5, because 5 times negative 1 is negative 5, and then you're ready to combine like terms. So negative 4 and negative 5 is negative 29, and negative 15 plus 8i is negative 7i. All right, down here we'll do FOIL again. So 4 times 4 is 16. 4 times negative 3i is negative 12i. 3i times 4 is positive 12i. And 3i times negative 3i is negative 9i squared. We have our I squared here. So we're going to eliminate that I squared and change the sign. Again, that's because we had negative 9 times negative 1 gives us positive 9. And then we'll combine like terms. 16 plus 9 is 25. I did that the last time I worked this problem out. 25 and negative 12 and positive 12 is 0. Those eliminate one another. So our final result is 25. Now, if you want, you could pause the video here and try these last couple of problems on your own, and then you could resume the video and check your work. I'm going to go ahead and continue working them. You could also choose to just work independently and tune me out, and then compare with me when you get finished. So negative 2i times 1 is negative 2i, and negative 2i times 4i is negative 8i squared. We've got that I squared here, which is going to change the sign of our 8 to positive. And then I don't have any terms to combine, but I'm going to go ahead and switch the order of those so that the real part comes first and then the imaginary. So 8 minus 2i. Last one, same thing. You can tune me out and try it on your own if you feel confident, or pause the video and work it out and then resume. So 3 times negative 5 is negative 15. 3 times negative 9i is negative 27i. Negative 2i times negative 5 is positive 10i. And negative 2i times negative 9i is positive 18i squared. I'm going to get rid of that I squared by, in my mind, I'm replacing it with negative 1, which is changing this to a negative 18. And then I have negative 15 and negative 18, which is negative 33, negative 27i, and positive 10i, which is negative 17i. That's it for multiplying complex numbers, so now we're going to move on to dividing. So if you'll look back up here at number 17, notice that the imaginary parts of the problem cancel each other out. They were inverses of each other. These two expressions are known as complex conjugates. Complex conjugates are in the form a plus bi and a minus bi. So the real parts have the same sign and the imaginary parts have opposite signs. So the same two terms, except the imaginary parts are opposite. And when we multiply complex conjugates, the answer is always a real number. So that's convenient. We like that, and that helps us on the next set of problems that we're going to work on. So here's an example of multiplying complex conjugates together. You have 2 times 2, which is 4, 2 times negative 4i, which is negative 8i, positive 4i times 2, which is positive 8i, and then positive 4i times negative 4i, which is negative 16i squared. Again, the negative 8i and the positive 8i eliminate one another. We have this I squared, we're going to switch the sign, and we get 4 plus 16, which is 20. So complex conjugates are nice because they cancel out the imaginary parts and give us a nice real number result. So let's take a look at some examples of complex conjugates. If I have the expression 2 plus 8i, then the conjugate of that is 2 minus 8i. If I have the expression negative 4 minus I, the conjugate of that is negative 4. You don't change the sign of the real part, but it's negative 4 plus I. And if I have a complex number that's just the imaginary part with no real, for example, negative 3i, then the conjugate of that would be positive 3i. We're going to use the complex conjugates to rationalize the denominator on quotients involving imaginary numbers and complex numbers, and so I'll show you how to do that coming up. So if you'll recall, in Algebra 1, you learned how to rationalize the denominator with an expression that had a radical on the bottom. So if we were working on something like 3 over radical 2, you know that you can't have a radical in the denominator of a fraction. So what would we do to make this better? We would create a perfect square on the bottom so that we could take a square root of it. So we would multiply by radical 2 because 2 times 2 is 4, and that's a perfect square. And whatever we do to the bottom, we have to also do to the top. So we would multiply the entire fraction by radical 2 over radical 2, and we would get 3 radical 2 on the numerator and radical 4 on the bottom. Our goal here was to create a perfect square so that we could take the square root of it and eliminate the radical expression on the denominator. We know the square root of 4 is 2, So that gives us a denominator of 2, and we end up with 3 radical 2 over 2. It's tempting to want to cancel out these 2's, but we can't cancel something that's on the inside of a radical with something that's on the outside, and the 3 and the 2 cannot simplify. So this is, in simplest radical form, we're not allowed to have a radical in our denominator. If you look at these examples under dividing complex numbers, we have i's on the denominators of these rational expressions, and I represents the square root of -1. We're not allowed to keep that square root on the denominator of our fraction. So what we're going to do is create that kind of perfect square situation, but we can't just multiply by a simple radical or even just by an I. We have to multiply by the complex conjugate of the denominator in order to eliminate those i's from the bottom. Remember, when we multiply by the complex conjugate, we get a nice real number answer with no i's left in it. So we're going to try that right now. All right, so here's example 20, and I've zoomed in so I have plenty, plenty of room to write. We're going to multiply by the complex conjugate of the denominator, and we're going to do that on both the top and the bottom. So remember, we're going to have the same 2 terms, but with the opposite sign for the imaginary part. So we're going to multiply by 3 minus 8i on both the top and the bottom. Now, both of these are binomials, so it's important that we recognize that we're going to have to either FOIL or use the box method for this. So I'm going to do the top first. And so here I go. 5 times 3 is 15. 5 times -8 is -40i. 2i times 3, that gives me -6i. And -2i times -8, that gives me positive 16i squared. That's going to become a -16. So I have 15 minus 16, which is -1, and -40i and -6i, which is -46i. So the numerator of my rational expression is going to be -1 minus 46i. Now I got to do the same thing for the bottom, aka denominator. So I've got 3 times 3, which is 9, 3 times -8i, which is -24i, 8i times 3, that's a positive 24i, which is what I expected, same terms, opposite signs in the middle, and then 8 times -8, that gives me -64i squared. My I squared is going to change my sign here because that's -1 times -64 makes a positive. These 2 middle terms eliminate each other, and here I get 73. So the denominator of my rational expression is going to be 73. And then there's nothing to simplify any further, so that is complete. For number 21, I'm going to use the box method just to show you that other way of doing it. We're going to start by looking at the denominator, and we're going to multiply by the complex conjugate. So that's going to be -1 plus 2i. We're going to multiply that on the top and the bottom of the fraction. Don't forget, you're multiplying both of these. So we're going to do a double distributive method again. This time I'm going to use the box. This is going to be for the top. Whoops. Guess I need to leave space to write it. So my terms are 3 plus 11i and -1 plus 2i. 3 times -1 is -3. -1 times 11i is -11i. 2i times 3 is 6i. 2i times 11i is 22i squared. Get rid of that and change the sign. So I have -3 and -22, that's -25. 6 minus 11i, that's -5i. So the top of my fraction is going to be -25 minus 5i. Now I'm ready to work on the bottom. So bottom, make my box. box. So I've got -1 minus 2i, -1, and positive 2i. -1 times -1 is 1. -1 times -2i is positive 2i. 2i times -1 is -2i. These, again, should be opposite signs, same terms, opposite signs because of the complex conjugates. And then 2i times -2i is -4i squared. These two are going to eliminate because they're opposites, they just cancel each other out. I squared is a -1, which changes this to a positive 4. So now I have 1 plus 4, which is 5. So my denominator is 5. Now this has an additional element that needs to be simplified. Notice that all of these coefficients are divisible by a common factor, and that common factor is 5. So we're going to divide all of the coefficients by 5. Oftentimes I will denote that by doing this kind of a thing to show that we're going to simplify all of those. We're going to divide by a greatest common factor. So the greatest common factor here is 5 in this case. So that is going to give us a simplified form. -25 divided by 5 is -5. -5 divided by 5 is -1i. And then 5 divided by 5 is also 1. This 1 on your denominator, it's not necessary to write it. Just like if I said, can I borrow $10? I wouldn't say, can I borrow 10 over $1? And I wouldn't say, can I borrow 10 ones necessarily unless I needed them to be dollar bills. But the 1 on the bottom isn't required if it's on the bottom. This coefficient 1 here, it's not necessary in front of the I, but if this front number is a 1, you need that there as a placeholder, so that can be kind of tricky. So in simplest form, this is going to be -5 minus 1i. All right, let's try this next one. Here we're going to multiply by 1 minus I and 1 minus I. The numerator here is just a monomial, a single term, so we're just going to distribute. And there's no need to FOIL or box there, so 5 times 1 is 5. 5 times -i is -5i, and that gives us our numerator. Then on the bottom, here I go. I have 1 plus I and 1 minus I. 1 times 1 is 1. 1 times I is I. 1 times -i is -i. And -i times -i is -i squared. So these two are the same term but with opposite signs, so they eliminate each other. This I squared is a -1, and -1 times -1 gives us +1. So 1 plus 1 is 2. So this gives us a 2 here, and we're done. We can't simplify. There's no GCF for all 3 of those. If it's only 2 of them, it's not okay. It has to be all 3 coefficients in order to simplify in that way. Here we are with number 23. If you feel super confident, you could go ahead and start working and then compare your answer to mine at the end, or you could even stop the video if you're watching on your own and then play it back when you're finished and see if you got it right. Here we go. We're going to multiply by 1 plus 2i on the top and the bottom. And that's going to require a little bit of extra work because I've got a binomial and a binomial. So here's my top. I typically find FOIL to be pretty easy, but when I'm doing so much of it here, for some reason, this box method really appeals to me, and I've had students really have a lot of success with it. So if you like organizing your work in that way, I would encourage you to kind of embrace that structure and use it to your advantage. So 1 times 8 is 8, 1 times 3i is 3i, 2i times 8 is 16i, and 2i times 3i is 6i squared. Your I squared is a -1, so that's going to make that a -6. 8 minus 6 is 2, and 16 plus 3i is 19i. So the top of my expression is 2 plus 19i. Now we're ready for the bottom. So 1 minus 2i and 1 plus 2i. 1 times 1 is 1. This is giving me negative 2i and positive 2i and negative 4i squared. So now 2i minus 2i gives me 0 for my I terms, and then I squared is a negative 1. 1 plus 4 is 5, so my denominator is 5. No common factor, so that's it for that one. Now number 24 is a little bit different because you notice the denominator is just the imaginary part. There's no real number here. So we're just going to multiply by negative 2i. Remember the complex conjugate, the imaginary part has the opposite sign. So we're going to multiply by negative 2i on the bottom and the top. Up here, we're going to multiply both terms by negative 2i. On the bottom, it's just one term and one term. So 6 times negative 2 is negative 12i. And then negative 3 times negative 2 is positive 6i squared. That is going to make that negative. And so we're actually going to have negative 6 minus 12i. So I switched the order so that it's real and then imaginary. And that's my numerator. So then the denominator, 2i times negative 2i is negative 4i squared. Your I squared is going to change the sign here and give you a positive 4. And then lastly, we have a common factor of 2 amongst all of these. So I'm going to simplify this with my GCF of 2. So negative 6 divided by 2 is negative 3. Negative 12 divided by 2 is negative 6. And then you got your I. And 4 divided by 2 is 2. Notice you could still divide these, but it's not legal to continue simplifying because they don't all three share a common factor. So this is the simplest form. All right, we're almost finished. It's number 25. So what do you think I'm going to multiply with the top and the bottom here? It's going to be positive 3i. Then we're going to continue in the same manner as we did on number 24. So we've got 5 times 3, which is 15i, and 6i times 3i, which is positive 18i squared. I would probably go ahead and simplify. That's going to give you negative 18 plus 15i. All right, now to the bottom. Negative 3i times 3i is negative 9i squared. Your I squared is going to change your sign and give you a positive 9. Here we have a GCF. They're all divisible by 3, so I'm going to go ahead and divide all of this by 3. So now negative 18 divided by 3 is negative 6. 15 divided by 3 is 5. We've got an I there. And 9 divided by 3 is 3. And that's how you rationalize the denominator with complex rational expressions. Now you're ready to start multiplying and dividing with complex numbers. Good luck!